Howdy everyone, Dr. Nir Regev here, and this time we're going to cover a paper called RadarCNN, Learning-Based Indoor Object Classification from IQ Imaging Radar Data. So they start by the abstract in the introduction, as always, and they cover what radar sensors in the millimeter wave frequency, what challenges they're facing, like, for example, indoors, you have a lot of multipath and multipath reflections, and that considerably distorts and confound the returning signal. And they present their machine learning based millimeter wave MIMO FMCW imaging radar object classifier using convolutional neural network, classification of small objects in an indoor setting, also with occluded environment, achieving 97 to 99% accuracy on a test set and almost 50% accuracy on occluded environment. And they start with the introduction here. Like they cover the applications. They say that these kind of radars are shown a lot in automotive applications, which is irrelevant for this specific paper. And indoor applications are limited due to this adverse effect, and usually people would like to use maybe cameras or LiDARs, but sometimes you can't. Due to privacy reasons, you don't want to get an image of the person. So the contributions for this paper include indoor radar data collection for hand-sized objects, dataset collection, adaptation of complex multi-channel time domain radar data for CNN input, and a modified CNN architecture suitable for processing IQ radar data. Okay, so they cover also related work here. They say that mostly the indoor radar applications are limited. Some work on indoor mapping and material estimation. And this paper builds on this by focusing on small-scale object classification requiring detailed information about the shape and surface reflectivity of objects. The radar that they're using is called imagVK74 radar, which has 20 transmit and 20 receive antennas. It's a virtual array, if I'm not mistaken, and it has a high resolution in both range as well as azimuth and elevation. Okay, next page. You see here that they are writing down how they collect the data. So the data is, they call it capital X, and it's N samples, in this case 100 samples, and since we have 20 receive, 20 transmit, we're basically have a tensor 20 by 20 by 100, and the objects that they want to classify is ceramic cup, laptop charger, computer mouse, pack of chewing gum, and a water bottle. We can see these items here in figure 2. And in figure 1, we can see the setup, and you can see here the radar is mounted here and looking down, and it's probably also various aspect angle that they move it on this mounting bracket right here with respect to the target. So this is mouse, this is a cup, and so on. Okay, so the proposed system, first they collect the data. This is the tensor for the data, 20 by 20 by 200, right? And then they do a pre-processing of the data. Sorry, the pre-processing, the radar data is basically shaped into a 400 by 100 pseudo data cube and fed into a CNN. The CNN consists of 3 2D convolutional layers, like an image kind of convolutional layer, followed by a fully connected layer with all the bells and whistles that we know already, for like batch normalization and so on. The real and imaginary part, if I'm not mistaken, as far as I can understand, is the channel of this image. So it's a two-channel image, one for real, one for imaginary. Okay, then they start. This is the architecture of the network. It's pretty straightforward. 3 hidden layers, convolutional neural network. And they start by introducing the confusion matrices, and you can see here that it misclassified a cup for a pack of chewing gum 5 times. It's 99% accuracy, and it's using only the real part of the signal. If it's using only the imaginary part of the signal, we have even less. It's 97% accuracy, and quite surprising, we have 98% accuracy if we're using both signal components, which I don't fully understand why. Maybe they didn't train enough, maybe the network cannot really deal with real and imaginary data, or cannot exploit the relationship and the phase between them, because in this case we have better accuracy with only real. Now they're doing some occlusion here, and we see that if it's only the real part of the signal, then excuse me, then they get a 45.5% accuracy. If it's only the imaginary part of the signal, it goes up to 51. And if they're using both of them in the occluded case, it's going back to 45. So again, real and imaginary doesn't give us anything, which is weird, because we don't lose information. We just present more information, which is probably confounding, maybe confounding the neural network. Maybe they trained it for too long. Maybe it's overfitting. I don't really know. Okay, and this is how they occlude. They put it inside a cardboard box, which is in the 60 gigahertz realm. By the way, they use a 60 gigahertz radar with 5 gigahertz or 6 gigahertz of bandwidth, and that's a fine range resolution right there. And this might introduce multipath due to this box here, and so this is why the accuracy drops. But the so to speak, the toss of the die accuracy that we expect out of a 5-class problem is 20%, and they achieve about 50. So that's something that is better. I don't know. This is it seems to me like very basic type of experiment and very basic type of neural network. Probably we can do a lot better than that if we kind of massage the data, maybe introduce also the frequency domain data, and other stuff that we can do. So thank you for listening. Subscribe and like, the usual stuff. Also, I'm going to post this and also a short summary of this paper in the Circuit of Knowledge under paper summaries. So stay tuned for this nice tutorial that is coming out. Thank you.